is what happens when you're technical support as well as the speaker. Yeah, and play. And that should be us. Okay. Welcome, everyone. It's my great pleasure today, this evening, to deliver this year's Priestley Lecture. And the title of my talk is The Hunt for Habitable Worlds. I'm going to tell you all about some first results from the James Webb Space Telescope, kind of in my capacity as someone who works at the interface between astrophysics, star and planet formation, and the study of exoplanetary formation and climate as well. And I am an astrochemist as well, so I'm a bit of a, I like to do a lot of different things, but it all comes really nicely together, actually, under this umbrella. So just a little bit about the relationship with Priestley. So of course the Priestley Lecture is named for Joseph Priestley, who you heard about just now. And he's really famous, I think, related to this lecture for his discoveries that confirmed the molecular nature of air. So back in the 1700s, they didn't really understand that air was actually made out of individual molecules and had different constituent molecules in it. And his isolation of molecular gases, such as molecular oxygen, for which he's very famous, but also nitrous oxide, nitrogen dioxide, carbon monoxide and sulfur dioxide as well, really set the foundations of modern climate science. And that is why our Centre for Climate Futures here at the University of Leeds is also named for Joseph Priestley. So of course, I'm not going to tell you all about Earth's climate today. I'm going to focus a little bit more on the climates of other worlds. So this brings me kind of to the big questions that we have when we're thinking about, is there life out there in the universe, and what processes might have happened to build a habitable planet? So one of the big questions that we have is, are we unique? You know, are we really the only planet that ever formed in the history of the universe that managed to have the conditions on its surface in order for life to begin and thrive? A second question is also related to our origins. Where do we come from? That's really about understanding the formation of stars and the formation of their planetary systems and the evolution of their planetary systems that might enable habitable conditions to actually arise on those surfaces. The final question, which is probably the most challenging to answer, will be, are we alone? I think that's something that humans have probably pondered about since they gazed up into the night sky, and is possibly the most challenging to answer, but we are trying to answer those questions. And I'm going to start very much and focus on this first question for most of this talk, but I'll come back to the last question at the end. And where do we come from? I can give a whole other talk about star and planet formation, but I don't have enough time to do that today. So I'm going to focus today on exoplanets. So let's first think about this question, are we unique? And are we unique in the ability of our planet to have had life emerge on its surface and indeed thrive? And to do that, we have to think a little bit about what actually is a habitable planet, what actually makes a planet habitable. And of course, the first example that we have of that is our beautiful planet that we live on, which is planet Earth. And we can kind of write down a few different key characteristics of planet Earth that kind of makes it what we think is a habitable planet. So of course, it's a rocky planet with a solid surface. It has an atmosphere and a temperature that allows liquid water to actually sit on the surface. And we know liquid water is very important for life. We are basically big bags of water and, complex molecules, essentially, when you break us down as human beings. It needs a nice temperature in order for that liquid water to be able to be sitting on the surface. We also need the surface conditions to have a low acidity. A high acidity would actually not allow large complex molecules to exist on the surface. We also need a stable atmosphere to kind of maintain those nice conditions that we have. And we also think that the fact our planet has a molten core and a magnetosphere is also an important component of its habitability. And I'm also going to come back to that as a metric as well. So we can look at all of these characteristics, but of course we have to remember this is coming from a very anthropic viewpoint, right? So this is what we see around us. Everything that we've dictated as being setting habitable conditions is really based on what we know, on our known limits for life on Earth. And one of the things that we really have to do is think about, well, is there other potential habitable conditions out there in the universe? But this is our starting point. So this is obviously where we start. And one of the things that we can start is think about these two conditions here. So the presence of liquid water and a nice temperature. And that brings me to this concept of what we call the habitable zone. Okay. So the habitable zone is a region around a star in which if a planet were there, it should have about the right temperature in order for liquid water to exist on its surface. So the water isn't in vapor form, it's not in gas form, it's a nice temperature just like our Earth, which allows water to sit on the surface. So if you look here, so the green region that you have in this video is the habitable zone around our sun. Okay, but of course our sun is a relatively rare star. So if you have a hotter star, the habitable zone will lie further away. But if you have a cooler star, so something that's smaller, has a lower effective temperature, which are much more numerous than sun-like stars, so 85% of stars are lower mass and cooler than the sun, then that habitable zone will lie much further in. Okay, and that's all related just to the energy output of the star. So when we're hunting for habitable worlds, how do we actually go about finding them? And how do we determine then if they're sitting in this habitable zone that they have around their parent star? So astronomers have come up with like very, very clever techniques to do this, some of which is very direct, just looking for light coming from a planet, and much of which is actually indirect, which is really looking at the manipulation of the planet's presence on the host star, which is much easier for us to see. So one of the methods, and I'm going to focus on two that we have here, one of the methods is called the transit method, and it exploits the fact that for some percentage of planetary systems, they're going to be edge-on to our line of sight. So we're going to have the planet, the star, with the planet orbiting directly in front of and behind the star. So that's what we mean by edge-on. Face-on would be, it would be orbiting in the plane. So when that happens, and the planetary system is edge-on, then when the planet actually passes in front of its host star, it will block a little percentage of light from that host star. And with very sensitive telescopes, we can see that percentage change. And you can see here in this little video that a smaller planet obviously blocks a smaller percentage of light than a larger planet. So by monitoring stars' light, looking for periodic dips that happen in a periodic way corresponding to the orbit, looking at the percentage of change in the star's brightness, we can actually really precisely measure the planet-star size ratio, because that's related to the percentage of light that's been blocked. And we can also get the orbital radius. So basically the semi-major axis is the distance between the planet and the star, because we know the duration of the transit. So this is remarkably successful and has been the most successful method to detect planets. But very much the workhorse of the early planetary detections was another method for which the Nobel Prize was won by Mayer and Cailloux. You might remember that a few years ago. So the Nobel Prize in Physics was awarded for the first detection of a planet around a main sequence star. And they exploited this method here called the radial velocity method. And this is a kind of an even more indirect method, if you like, and it exploits the fact that when two bodies are in orbit about each other, it's not that one is static and one is orbiting, they're orbiting about a common center of mass. Okay. Now, there's more people coming in, even though they're late. So this video kind of, it shows you what's happening. So you have a star in the center and a planet. These are not to scale, it's just for emphasis. Star in the center and a planet orbiting it. So because they're orbiting about a common center of mass, when they, so the star is kind of orbiting as well. So it's going away and towards us on a little orbit. So when the star is coming towards us, the very fine spectral lines being emitted by the star, they get blue shifted to a higher frequency or a shorter wavelength. When the star is moving away from us, those lines are red shifted to a lower frequency or a longer wavelength. Okay, you can kind of see that here. So you have these absorption lines in the spectrum of the star, and they get shifted in wavelength and frequency as the star is moving, as its position is being perturbed by the planet. And this is what we call the radial velocity method. It's basically Doppler shifting, similar to a siren going past you, and it increases in pitch as the siren approaches and decreases in pitch as it moves away. It's exactly the same principle, except with light. So this is another very powerful technique. So although we're not seeing the planet directly, we can get a lower limit to the planet mass. That's because we can use this technique even for planets that are on an inclined orbit. So we don't need the planet to be passing in front of the star. We can get also the orbital parameters. But very often what we do is we combine these two techniques. So we do the radial velocity method on planets that are found using the transit method, and we can basically fully characterize the planet. Okay, we can get its mass, we can get its radius, we can get its semi-major axis, so the distance at which it's orbiting from its host star. That allows us to determine its temperature, its average temperature. We can get also its eccentricity and inclination, because the shape of the perturbation or the shift in frequency of the lines is very related to the parameters of the planetary orbit. So with these two techniques, we can fully characterize the planetary system. So once we have the planet mass and we have the planet radius, what we can do is we can actually then characterize the density of the planet, which I'll come on to. So I want to introduce you here to this telescope called Kepler. I don't know why that's blinking, but we're just having all of the issues today. So this is the Kepler Space Telescope, and it was a telescope that was designed to detect planets using the transit method. And it was designed specifically to stare at very faint stars, so those lower mass, cooler stars than the sun, okay, for which, remember, the habitable zone sits closer to the star. So to give you an idea of how powerful Kepler actually was, so here what you're going to see is a distribution of planets that have been found as a function of their orbital period in days, and then the size of the planet relative to the Earth. So on this side you have the Earth here, this is Neptune, which is about 4 times the size of Earth, and then we have Jupiter, which is 11 times the size of Earth, just for reference. So this is what Kepler found. So this is the detection statistics from around 2017, when really Kepler was in its prime era. So in yellow are all the planets that are found by Kepler, and in purple and blue are the ones found before Kepler. So they numbered in the hundreds. Once we had Kepler, planets that we detected then numbered into the thousands. Okay. And as you can see, before Kepler, we mainly found these larger Jupiter-sized planets in the purple and blue here. Once we had Kepler, which was much more sensitive, then you can see we started to get down to start to find these Earth and Neptune-sized planets. But you'll notice we do have this empty corner in the bottom right-hand side, okay? So this is the number of planets we've found so far. So this is now 7,354 planets as of a couple of days ago. So this is where Earth sits. This is an Earth-sized planet in an Earth-like orbit, and we're still not finding planets like that, okay? This is really what we would call the frontier. We see Earth-sized planets much closer to their star, but we certainly don't see Earth-sized planets at 1 astronomical unit where we are around the sun. And that's just due to biases in our detection techniques, which are more sensitive to finding larger planets or planets which are orbiting closer to their host star. But nonetheless, I think in the next few years, we're going to breach 10,000 planets. So once we have the planet mass and the planet radius, then we can get another fundamental property of the planet, which is its density. If we know the density, then we can determine, is the planet rocky, like Earth? Is it mainly gaseous, like Jupiter? Or is it something that's a little bit in between? And that's exactly what we do. And of course, we classify things by what we know. So this is, again, the same data from Kepler that you see here. You have the orbital period, again, in days on the x-axis and the size relative to Earth on the y-axis. You can see here in yellow all the rocky planets that were discovered. Some of these orbit so close to their host star that their surface should be molten. It will be thousands of Kelvin, which is enough to melt rock. So these are lava worlds, and we see evidence of that. If we move up in size, we also see Neptune-sized worlds. Some of these are orbiting at around the orbit of Neptune, so they're the ice giants, just like we have in our solar system. Some are orbiting much closer to their star, so they would be ocean worlds. They have a lot of water, perhaps, in their atmosphere. And if we jump up in size again, we can see these cold gas giants of a similar size as Jupiter, but we also have this population of what we call hot Jupiters. So these Jupiter-sized and Jupiter-mass planets that are orbiting very, very close to their host star with orbital periods on the order of just a few days. So these are really, really close-in planets. And of course, here is our frontier. This is where we want to push our detection techniques down to see if we can find more terrestrial-like planets like we have in the solar system. Okay, now what's really interesting, so we've had these 7,000 planets, and what you're looking at here, so this is the size of the planet relative to Jupiter, so Jupiter would be here, and this is the number of planets that we have found in each of these size bins, okay? So the most common type of exoplanet that we find, we don't have one in our solar system, right? So here's the Earth, that's about 9% the size of Jupiter, and here's Neptune, which is about 34% the size of Jupiter. And you'll see that the peak in the distribution, the most common type of exoplanet, actually sits in between these two sizes. These are what you might have heard in the literature and the news called sub-Neptunes or super-Earths, because again, we classify everything by what we know. So the most common type of exoplanet, we don't have one in our solar system. And that's reason, again, questions on our uniqueness. If we don't have one of the most common types of exoplanets that we find out there, does that mean that we are actually quite a unique composition for a planetary system? We're not typical. One of the caveats of this distribution is that it's harder and harder to find smaller and smaller planets. So we really don't know what this distribution looks like down here. So again, trying to push to smaller planets, to Earth-sized, Mars-sized, even Mercury-sized, we'll be able to see if this distribution is true or if we have as many kind of Earth-sized planets as we do these super-Earths and sub-Neptunes. So from the rocky planets that we found, and Kepler has found a lot of them, are any of them potentially habitable? So if we look at their host star, we look at their average temperature based on the distance that they are from that host star, we actually have found about 29 potentially habitable worlds, okay? So these are rocky planets that are predominantly found around cool stars, so stars at lower mass, lower temperature than the sun, and which have a equilibrium temperature, as we call it, which, should their atmosphere allow it, would allow liquid water to be hosted on the surface. So although we're still kind of in the early days of finding planets, we still don't have complete statistics. We still have a lot of biases in our detection techniques. We have now discovered 29 habitable planets and counting. So we add a few of these onto our classification every year. And these are really prime targets for JWST. Some of these potentially habitable planets are actually in multiple systems. So there's the TRAPPIST-1 system, which I'll tell you about. There's the JG1061C and D planets as well. So for some of these planets, there are several planets in their planetary system that are also potentially habitable. So let us kind of go back to our characteristics. So here's our Earth again, okay? And this is our list of habitability metrics. So at the moment, everything that we've considered is really just whether or not the planet might have the right temperature to host liquid water on the surface. But one of the things that's really important in setting the surface temperature of the planet is actually its atmosphere. So yes, we can find these potentially habitable rocky planets based on this equilibrium temperature, but really what we want to do is we want to try to detect if they have an atmosphere, and if they have an atmosphere, detect its composition. Because we all know of our evil twin, which is Venus. So Venus actually orbits within the inner edge, or just at the inner edge of the habitable zone around the sun, but you do not want to go and live on Venus. The surface conditions are about 700 bar. You would be crushed. You wouldn't be able to breathe. And the temperature is like it's hundreds and hundreds of Kelvin. So it's a really hostile environment, and that's because of the molecular composition of Venus's atmosphere. It's the CO2 really in Venus's atmosphere that has driven this runaway greenhouse effect and created very extreme surface pressures and temperatures. So we want to detect an atmosphere, but we also want to consider what it's made out of, because that's really what's going to set the surface conditions. So the question is, can we actually do this for exoplanets? And this would be a very short talk if the answer was no, because I would just finish here. So of course the answer is yes, we can. And we do mainly do this for gas giants. To do this for rocky planets is incredibly difficult. And this is why. So this is Earth. It's a picture taken by an astronaut on board the International Space Station. And that blue ribbon that you see here, that's our atmosphere. So everything that's protecting our surface from the harsh radiation from the sun and also from space as well is really all in that little thin blue ribbon. So if we want to see the atmospheres of rocky planets, we're trying to find this very, very tenuous kind of sheath, if you like, of gas that's sitting around a much bigger rocky planet. So we can detect exoplanet atmospheres, and we have been doing this now for quite a few years. And we have been doing this by exploiting the fact that, so I've already introduced you to the transit method. So when a planet passes in front of its host star, you then see a dip in the light curve that is related to the size of the planet. Now, if a planet has molecules in its atmosphere, and those molecules absorb radiation at very specific wavelength ranges, then what should happen is that the size of the planet should change as a function of wavelengths. That's what you're seeing here. So this little cartoon planet, it has titanium oxide and water in its atmosphere. So by taking and measuring the transit depth as a function of wavelength, we can then see a change in the size of the planet because there's water there. So at the wavelengths that water absorbs strongly, the planet looks bigger because of the presence of water. And then out of those wavelength ranges, the planet looks smaller. Does that make sense? So the fact that you have molecules in the atmosphere will change the size of the planet. And that's exactly what you see here, what we would call a transit spectrum. To kind of make this a little bit more pictorial for you, I'll show you a little video. But just to let you know, like some of these molecules that we're looking for are, of course, water, things like carbon monoxide, simple molecules, things like methane, which is a proposed biosignature because it's made mainly by life on Earth. And if we're looking for Earth-like exoplanets, of course, we want to try to find the presence of molecular oxygen as well. So this little video kind of demonstrates what's going on. So what you're going to see is this little cartoon planet here. It's going to pass in front of its host star, and you'll see the change in the light curve at these three different wavelengths, so 1.8, 2.1, and 2.3 microns. So you can see that the planet looks a lot bigger at 2.3 microns and at 1.8 microns than at 2.1 microns. So it changes in size. And the fact that it changes in size and looks bigger at 2.3 microns is a very strong indication that there's water in this atmosphere. That it also looks a bit bigger at 1.8 microns tells us that there's methane in this atmosphere. So we're really just exploiting the fact that molecules are very, very good at absorbing radiation into their kind of vibrational modes. And this is how we detect the presence of molecules in the atmosphere. So this has been most successful for these hot Jupiters, so these very, very massive planets that are orbiting very, very close to their host star. These were the first types of planets that we actually found. And I'm going to show you just a few slides of what we've been able to do in the pre-JWST era. So very much the workhorse for characterizing exoplanetary atmospheres was done by Hubble, so the Hubble Space Telescope, which is still operational now. We still use it to do the same work, but also the Spitzer Space Telescope as well, which operated in the infrared. So that was the previous generation of infrared observatories. You see here a compendium of different hot Jupiters, going from very hot Jupiters to cooler hot Jupiters. You're looking at the light being emitted by the planet, which is related to its ability to absorb molecules. So basically, so the light being absorbed by the planet is a function of wavelength, and the dots that you see here are the data, and the lines are model fits to the data. So in astrophysics, we do a lot of modeling and a lot of modeling fitting in order to make robust conclusions about the data that we're looking at. We're very often dealing with very weak signals, so we have to use a lot of computational modeling to rule in and out different hypotheses. So Hubble was really, really successful. So the data you're looking at here is mainly Hubble in the visible wavelength range. And I'll just point out here that, so if you look here, so Hubble was really successful at finding water in exoplanetary atmospheres. Water alone is not a criterion for habitability. Water is everywhere through the galaxy. It's really easy to make water. It's liquid water that's really the issue. But nonetheless, the fact that we were detecting water allowed us to derive a lot of characteristics about these hot Jupiter atmospheres, especially to compare with our Jupiter, which is a cold Jupiter, which is orbiting up out there at 5 AU. So Hubble was really, really successful, but of course, these are hot Jupiters. These are not habitable planets. So we learn a lot about these gas giant planets. We don't learn anything about habitability. So Hubble did try to push to smaller and smaller planets. So it was successful at observing a few of these, what we call warm Neptunes. So remember, these are Neptune-sized, Neptune-mass planets that are orbiting quite close to their host star. So they're warmer than Neptune. And that's a little cartoon of what Neptune looks like there. So again, this is Hubble data. So the points are the data taken by the telescope with their error bars. And then the lines that you see are, again, model fits to the data. And again, you can see that the planet looks bigger at this wavelength of 1.4 microns, which is a very well-known absorption band of water. So that's a concrete detection of water in this warm Neptune called HAT-P 26b. They don't have very interesting names, a lot of these. I'll tell you where they come from if you're interested. But yeah, very concrete detection of water, and we could rule out the presence of things like methane and CO and CO2 from the Spitzer data. But again, this is not a habitable planet. This is a mainly gaseous planet. Okay, and the fact that we find water is interesting, but doesn't tell us anything about its habitability. And then probably one of the more interesting for what we're going to talk about today, results from Hubble, is Hubble looked at a super Earth called K18b, or K218b. Super Earths are, again, these, we think, mainly rocky planets, or at least a lot of their mass is made out of rocky material. So they're a few times the size of the Earth. So here's an artist's impression of what a super Earth size would look like relative to the Earth. And this is, again, this K218b. This is a super Earth planet. This is Hubble data again, and here's this 1.4 microns. The points are the data, the blue lines are fits to the data, and again, they were able to find this very nice signal of water in the atmosphere of this super Earth. So what's actually now interesting about K218b is, from the first atmospheric results I've shown you, it is actually a planet that's orbiting in the habitable zone around its parent star. Okay, so the warm Neptune and the hot Jupiters that I showed you before are way, way far in. They're really, really hot. But this is a temperate planet. This is a planet with an equilibrium temperature of about 300 Kelvin, about 20 degrees centigrade. Okay. But this was very exciting at the time. The media back in 2019 got very excited. This ended up in Nature, lots and lots of fuss about it. But the community kind of, pushed back a little bit on this result, because this is most likely not a habitable planet. So K218b is a super Earth planet. It's 2.2 times the size of Earth. And that's just in this fuzzy region where it could still have a very large hydrogen-helium envelope. It's massive enough to hold on to a primordial envelope. So we still don't know for sure that this detection of water is actually in a rocky planet with a water-rich atmosphere. And there's still a lot of debate going on its nature, which JWST has been able to reveal a little bit more. So that was kind of a little flavor of what we knew about exoplanetary atmospheres before JWST. So now to kind of get to the main event. So this is the James Webb Space Telescope. This is what it looks like. It is out at the Lagrange point L2, along with a lot of other telescopes that we put out there. It is a passively cooled telescope. So it's got a sun shield here, which basically keeps the optics and everything shielded from the sun. So that's why it's able to very efficiently observe the infrared universe. So where does JWST actually observe the universe? So here is Hubble that I've introduced you. Hubble was predominantly a UV-vis, what we call telescope, so operated in the ultraviolet and visible. Visible wavelengths is the light that we observe the world at. Spitzer, which also did a lot for exoplanets back in the day, is much longer infrared wavelength light. James Webb fills in this really nice gap in between the two, which is a really important wavelength range for astronomy. If any of you are interested in high redshift galaxies, that's why we have JWST. If we want to see things, that were formed just after the birth of the universe, all of the visible wavelength light gets redshifted into this wavelength range. This is really what JWST is designed to do. For the science related to stars and planets, however, it's also a very powerful telescope. So why do we observe in the infrared light? It can travel through the interstellar medium much easier than visible light. It's less scattered and absorbed by dust grains. That gives us a deeper view through galaxies and within our own galaxy. It probes the warm universe, including us. So if you work out the peak of the wavelength at which the Earth emits most of its radiation, that's actually in the infrared. So we're very bright in the infrared, which is also why you need to put James Webb out in space to get away from us as well. So it probes uniquely this universe. And finally, which is related to astrochemistry, which is what I mainly do as my day job, it's a very powerful probe of composition, because molecules, including molecules in atmospheres, can absorb and emit light very efficiently at infrared wavelengths through what we call the vibrational modes or low vibrational modes. And it can do this in the gas phase and also in the ice. It can see the solid phase as well. So it's a very powerful probe of the composition of material in the galaxy and beyond. So to give you a view, because with exoplanets, I can't show you many nice images, so I thought I'd show you at least one really nice image from JWST. So this is the Hubble image of the Pillars of Creation in the Eagle Nebula. This is one of the famous Hubble nebula images. I've had it up as my background laptop screen at some point in the past. And what you're looking at here is bright nebula emission from scattered light from nearby massive stars. And in the foreground, you see these kind of large pillars, very highly sculpted pillars of dust and gas, which are very dense, and they're obscuring all the light from the background stars. So this is the visible wavelength light. If we switch on JWST and look at it with the infrared, it looks very different, okay? So you see this really rich background star field that's completely obscured by the nebula emission in the visible. You can also see through some of these columns. You can also see into them, and you can see forming stars, especially happening at kind of the tops of the pillars. The other thing that's interesting from my perspective, interested in star and planet formation, is some of these regions are still opaque at infrared light. So these are some of the most dense regions within which probably young stars are forming. So in the infrared, we get a very different view of star forming regions of our interstellar medium than we get with visible wavelength light. And that's why it's so powerful. It can also see ice, which is really powerful as well. And this is a really nice first result from one of the early science release programs from JWST. So what you're looking at here is a spectrum, very much like I've shown you before for the exoplanets, except where you see a dip now is corresponding to the detection of the molecule, okay? So we have wavelengths of light here along the x-axis. We have the brightness of the light as a function of wavelength. And where you see these deep dips corresponds to, again, distinct wavelength ranges that molecules in the ice phase are absorbing at. So we have a clear detection of water ice here. We have methanol ice here. Very clear detection of carbon dioxide in the ice phase as well as some other carbon, sulfur, and nitrogen-bearing species. So JWST is allowing us to probe the composition of the very icy material in interstellar medium, showing us that even kind of small, simple organic molecules, chemistry is able to occur in these very cold and extreme regions. So this is why JWST is such a powerful instrument. But what's it actually doing for exoplanets? Because that's what we're here to talk about today. So we can actually directly detect light from exoplanets, and we can only do that if we somehow mask the light coming from the star. Because the star is so much more brighter than the planet, we really need to try to block it in order to see the light from the star. And this is the direct detection with JWST of this planet here, HIP or HIP 65426b. It was done at 4 different wavelengths, so that's why there's 4 different images here. The star is actually here in the images, and this has been done using a technique called coronography, where you have a little disc attached to the telescope. You point your telescope so that the star is behind the disc. That blocks the light from the star and then reveals the light coming from any point sources that would be nearby that very, very bright star. Okay, so you don't see the star, that's actually been blocked by the telescope. And this is a really powerful technique, especially if you do it over multiple wavelengths. You can kind of reconstruct what we call the spectrum of the planet. You can infer then its mass, you can infer its temperature, okay? And what they find out about this planet here is it's actually particularly massive. It's about 6 Jupiter masses, so much more massive than our Jupiter. When they looked at the flux of light coming from the planet at these 4 wavelengths, they worked out its temperature was about 1200 Kelvin, so much, much hotter than Jupiter. The interesting thing, it's about 100 times further away from its star as we are from the sun. So it's at 100 astronomical units, which is 20 times further away than Jupiter is from our sun. So how can it be 1200 Kelvin? And the only way that it can be that hot is if it just formed, if it's a really, really young planet. Because as planets form, they contract and cool. And it's that gravitational contraction goes into heat, which is then irradiated away. So a really powerful technique. And the reason that these don't look like point sources in the images is due to the refraction and bending of light as it goes past the coronagraph and into the optics of the telescope. Of course, this is not a habitable planet, but does showcase JWST's power to actually directly detect light from exoplanets. So this will be exploited for a lot of these far out Jupiter mass planets. But what about the transit spectra that JWST is observing? So the very first early science result was done on kind of a planet that they knew they would get good data with. So they picked a hot Saturn. So a hot Saturn mass planet. This was called WASP-39b. You've seen a lot of these spectra now. So this is wavelength on the x-axis. This is the amount of light, or the size of the planet, if you like, as a function of a wavelength of light. And they picked WASP-39b because they already knew there was water in the atmosphere. So they knew they would definitely see something in the atmosphere of this planet. So it was already observed with Hubble. And what they found was really surprising. So they also got the signature of water, which you see here and here, but they also saw signatures of carbon monoxide. They saw signatures of carbon dioxide, which is a very common constituent in the atmospheres of the planets in our solar system, and also a really nice detection here of sulfur dioxide. Now, Hubble was very powerful, Spitzer less so, and there had been claims previously of the detections of methane and carbon dioxide and other atmospheres that had been refuted in the literature for decades, with people arguing over the sensitivity of the data to those features. So with JWST, that really was the first concrete, undisputable detection of molecules other than water in an atmosphere of an exoplanet. So really important also for characterizing and trying to understand the physics and climate of these very hot gas giants. Gas giants are interesting, but they're not habitable planets. So why don't we try to go to more habitable-like planets? So you've met this planet before. This is K2-18b. This was a planet that had the concrete detection of water with Hubble. That was also the super-Earth planet that's orbiting in the habitable zone around its host star. So this was a key target for early science with JWST as well. And what was really interesting was that we saw the first concrete detection of methane for the first time. We see an absorption band of carbon dioxide here as well. And methane's interesting because we think it can be formed abiotically in these more gaseous atmospheres, but on Earth it's considered a biomarker. And then the authors also claimed a detection of dimethyl sulfide, so DMS, which is only produced by life on Earth. So methane is disputable, but DMS, dimethyl sulfide, is only produced by life on Earth. So really exciting, and again has made a big splash in the media. So you may have seen this in the media in the past year, but did for the first time really show that there's methane in some of these atmospheres, and this tentative detection of DMS was proposed as a potential biosignature in this super Earth. So there's a lot of debate raging in the literature, again, as often happens when these claims are made. So in order to show that DMS or dimethyl sulfide is really a true biosignature, you would have to prove that it can't be formed any other way. So it can't be formed just by simple chemistry that might happen. And of course, people have already weighed in and showed that this can happen. So this is a comet. Comets are leftover icy remnants from the formation of the planets in the outer solar system. You hopefully all know comets. When they come in to visit the inner solar system, they get warmed up and have these beautiful coma and tails, okay? That's sublimation of ices from their surface as they warm up by the sun. So this does come from a media report from a conference, a press release through the European Geosciences Union just this year. And they've gone back and looked at some data from an orbiter called Rosetta, which was able to measure the composition of 67P, so this comet, and they find a signature of dimethyl sulfide. So they basically say you can form this easily in planetary systems, you can form it on a comet. To say that it's a biosignature, it's a little bit extreme, okay? But I'll come back to biosignatures towards the end. So K218b is not still a gas-dominated planet. What about rocky planets with JWST? And this is where we come back to this interesting system. So this is a TRAPPIST-1 system. This is a cartoon of what it looks like. Here's its tiny star relative to the sun, and it's got 7 planets. And if you look at their orbital radii, they're all orbiting relative to our sun within here. So they're all orbiting their star well within the radius of Mercury around our star. Okay, this is a very weird planetary system, and it's a very small star. If we compare the planetary system with Jupiter and its major moons, you can see it almost looks like a moon system rather than a planetary system. But TRAPPIST-1 is really interesting because it's one of the closest systems that we have, where we have 4 planets that are orbiting in the habitable zone around this star. Okay, so because of that alone, because it's quite close and nearby, I think more than 300 hours of JWST time have been dedicated solely to this planetary system. And I'm going to show you 2 of the results today, but there will be many, many more results to come. People are working on a lot of data on the system. So what's the first result? So the first result was they went and they observed the innermost planet, B, because that's how we name them, B, C, D, E, F. So the innermost planet is B. So that's the one that's closest to the host star. And what they did was they measured the flux of light coming from the star just before it passed behind the star in what we call secondary transit, okay? So they looked at the light and they estimated the planet's temperature. And they estimated the planet's temperature to lie about here. So they have this in Fahrenheit because it was an American press release. But this is corresponds to 500 Kelvin, which is 430 something Kelvin, 420 something Kelvin. So that's the temperature of the planet that they measured. They then compared that temperature with 2 different models, one where the planet is just a hot rock with no atmosphere, and one where it has an atmosphere, because the temperature of the planet will be different, okay? So if you have an atmosphere and you're being irradiated by a star, the atmosphere will carry heat all around the planet. So the temperature that you would have on that planet will be, on average, cooler than if you have no atmosphere at all. Look at the moon. The sun side of the moon is hundreds of degrees warmer than the dark side of the moon, okay? Because there's nothing to redistribute the heat. Rock does not do that. So what was quite sad was they confirmed that TRAPPIST-1b is as a hot rock. So the model that best matches their data is a dark surface with no atmosphere and no redistribution of heat. So it's starting to kind of raise questions on the ability of these TRAPPIST-1 planets to be able to retain an atmosphere. But of course, this is the innermost planet. They've also, and it's not a habitable planet because it's not in the habitable zone, and it's certainly not a habitable planet if it has no atmosphere. So they have looked at the second most farther out planet, so TRAPPIST-1c as well. And these authors did the same thing. So they measured the light coming from TRAPPIST-1c just before it passed behind the star. And they looked at it at a particular wavelength, which was 15 microns, okay? So this is the brightness at this particular wavelength. So the single point here is the data. This is what we're dealing with, okay? This is the data. And then what they did was they compared the data with 3 different models. So the yellow model here is a thick carbon dioxide atmosphere, which is very Venus-like. The green model is a bare rocky surface with no atmosphere, so very much what was assumed for TRAPPIST-1b. And then the blue model is a very thin carbon dioxide atmosphere with no cloud, so something that might be akin to what Mars's atmosphere is, for example. And you can see here, based on the error bars, that it's inconclusive. They can rule out that it has a thick atmosphere like Venus, but they cannot rule in or out the presence of an atmosphere versus bare rock. So again, we're thinking that these planets may not have atmospheres. And again, even if it has a very thin atmosphere, that would not make it habitable. So why are concerns being raised about the TRAPPIST-1 system? So this is the size of TRAPPIST-1 versus the Sun. So this is what we call a cool M-dwarf star. Some people call them red dwarfs as well, because they're very red. The peak of their electromagnetic spectrum, their black body spectrum, is very much in the infrared. And even though they're very small and they're very cool, they're much more active stars. They have much more magnetic activity because they're convective stars, okay? That means that they actually throw out a hell of a lot more radiation at short wavelengths than something like the Sun would do. So this is a simulated spectrum of TRAPPIST-1 versus that of the Sun. This is the high energy radiation end. This is the lower energy radiation end. And scaled to the same flux, same radiative flux, TRAPPIST-1 is a significantly more energetic star. It has a lot more radiation at what we call X-ray and extreme UV. And this is catastrophic for atmospheres. This actually is what strips atmospheres away. So we're starting to get raising some questions on the abilities, even for rocky planets, to hold on to their atmospheres around these very active M-dwarf stars. And remember, 70% of all stars are these M-dwarfs. They're going to be the most common planetary host. So that comes back to kind of our habitability criterion. Okay, so you've seen this a few times before. And of course, for life to be able to arise on a surface, we need a stable atmosphere. And one of the things that we think helps our Earth hang on to its stable atmosphere is also a magnetosphere as well. So if these TRAPPIST-1 planets don't have a molten core, they don't have a magnetosphere, it's possible they're not able to protect themselves against the very harsh radiation coming from their star. And that would, over time, over a giga-year, strip away the atmosphere. So our magnetic field plays a very important role in our habitability. It protects our atmosphere and us on the surface from the solar wind. Okay, so I'm nearing the end. That's kind of the end about the exoplanets. But to summarize, we've not yet detected a true exo-Earth analog, and we've not yet detected the atmosphere of an Earth-sized planet in its habitable zone. This is still kind of really in the frontier of what we want to do. So at the moment, it really does look like, from what we know already, that we are unique. But of course, the question is not closed. It's still an open question. So as astrophysicists, we're still thinking about the future, and we always have in mind what the next facilities will be. I'll just highlight a few of them here. So we are currently building the extremely large telescope in Paranal in Chile. It's a 30-meter telescope. It will be much more sensitive and have much higher spectral resolution than anything we've had on Earth before. It's going well, its construction, it's expected to have first light in 2028. So the ELT has been designed with instruments that should be able to detect and characterize the atmospheres of rocky planets and look for these types of compounds, things that we call biosignatures. But what is a biosignature is a bit of an open question. But people are predicting that the ELT should be able to distinguish an early Earth from a current Earth, a super Earth from a mini Neptune, and also an Earth-like atmosphere from a Venus-like atmosphere. But again, trying to find signs of life on these planets comes down to what we determine to be a reliable biosignature. So a signature, a combination of signatures that only can arise from life alone. And that's a big open question. So this is not my field of research, but astrobiologists are really working on this and are starting to try to come up with combinations of signatures, including false positives. So don't try to take in all of this information. I'll just highlight here. So if you were to try to determine an Earth-like atmosphere where the oxygen and methane was arising from life, then based on what we know about the chemical mechanisms in our atmosphere and the geochemistry, we should be able to detect oxygen, ozone, water, CO2, and methane, but we should not see CO. We should not see carbon monoxide. If we were to see carbon monoxide with these other tracers, that's a clear indication of abiotic sources of oxygen and methane. As another example related to TRAPPIST, if you had a habitable CO2-rich planet orbiting an M dwarf, again, if life were present on the surface, we would see these combinations of positive signatures. But if we were to detect methane in conjunction with these, then that would rule out, again, a biotic source. So this is really, really difficult to do because all of these molecules can be created just by chemistry in atmospheres. So they're working really hard to try to come up with concrete determinants of what is a biosignature. So we're trying to find more planets. So we have the PLATO mission, which will launch next year. It's got a giant array of cameras, stands for Planetary Transits and Oscillations of Stars. It is designed to find Earth-sized planets around sun-like stars. So with PLATO, we'll get planet detections up into the tens of thousands, and it's predicted to find about 500 more Earth-sized planets. So again, in the next decade, we'll have much better statistics on our planet size distribution. We're still exploring the solar system, so Mars is still a big target to look for current or extinct life. We have the Mars orbiter, which is already orbiting Mars and surveying it from orbit. The ExoMars rover will go up in 2028. And of course, we have Perseverance, the NASA mission that's been there for a few years now. And both of these rovers are equipped with probes to dig down to really get deeper than we've done before in the surface before to really see if there's any extinct or current life. So we're still exploring Mars. What about further afield? Well, you may have seen this last year, a few years ago now. So there has been a claim of a detection of phosphine on Venus. Phosphine is another biosignature on Earth, produced mainly by life. The authors argued in this detection that it could be a sign of microbes in the cloud deck of Venus, not on the surface, because the surface is too inhospitable, but possibly in a more temperate region, higher up in the atmosphere. So this has been raging a debate in the literature for many, many years now with a lot of skeptics, and I know more data is coming. It's data led by Cardiff, actually. There's more data coming that hopefully will be more conclusive, but it has actually enthused space agencies to go back and explore Venus again. So we have this Da Vinci mission, which will be launched in 2030. It's led by NASA. There will be this probe, Da Vinci Plus, which will be launched from an orbiter and will descend down through the cloud deck and then reach the surface. It will be a sacrificial probe because it will be crushed within 20 minutes of landing on the surface. But because it's talking to the orbiter, it will be able to relay all of its information back to the orbiter. It doesn't have to get all the way back to Earth. So it should have enough time to send back all of the information about the physical conditions and the chemistry and the molecular composition of the atmosphere to the orbiter before it is sacrificed. We have the icy moons of Jupiter. So we have Io, Callisto, Europa, and Ganymede. These are of great interest because they have evidence of subsurface oceans. So in Europa, we see water plumes through the cracks detected with Hubble. With Ganymede, we see oscillating auroral belts that give an indication that the inside is fluid, so a subsurface ocean. And the icy moons actually fulfill some of our criterions of habitability. They have a surface which protects their water or their fluid that's internal to that from ionizing radiation, and they have a temperature inside them that allows water to exist as a liquid. So the fact that these have subsurface oceans actually makes them a big target for exploration. And there are two missions. So one of them is JUICE. JUICE is en route to Jupiter. It will arrive in 2031. Stands for Jupiter Icy Moons Explorer. It has a suite of instruments, so spectrometers to look for light, magnometers to measure magnetic fields, radar to map the surfaces of the moons. So it will really tell us a lot about the icy moons of Jupiter. And then just a few weeks ago, I think on the 14th of October, NASA also launched the Europa Clipper mission. That will actually arrive before JUICE in 2030. So they're utilizing a swing by Mars to kind of overtake them. So that's why that happens. So you don't go in a straight line to the outer solar system. You have to take a complicated route. This will focus mainly on Europa because of that evidence of water plumes from its surface. It will also have a mass spectrometer on board. So if there is organic material that's being ejected from Europa Clipper will detect it. And if it's of prebiotic or biotic importance, we will know. So again, in the next couple of decades, we'll get a lot more information about the icy moons. So we also have Titan. Titan's interesting because it's a moon around Saturn. It's actually the only moon with a substantial atmosphere. It's much, much colder than the Earth, but the pressure at the surface is only 1.5 bar. The atmosphere is mainly molecular nitrogen with a bit of methane. So it actually has some really interesting atmospheric chemistry. It has water on its surface, or not water on its surface, it has liquid on its surface, but that liquid is methane, not water. So again, thinking outside the box, should we be exploring these other kind of potentially habitable environments? We have this Dragonfly mission led by NASA. This isn't what Titan looks like in the visible, it's completely opaque, but for media, I suppose it works. It will be a little lander drone, so it will actually fly around because the pressure is enough to fly about. It's very difficult to do on Mars, but you can do it on Titan. Little lander drone, again with a suite of instruments to kind of probe the surface composition, go to the methane lakes, work out kind of the orography and the composition of Titan's surface. And again, that will launch in 2028. So we're doing a huge amount also in the solar system, and I still don't think that we have fully concretely explored all potentially habitable conditions closer to home. So just to finish, I have this final question, are we alone? I'm not going to answer that, but I am going to give you some numbers that hopefully will give you some food for thought. So here's the Milky Way. It's an artist's impression because we're inside the Milky Way, so we cannot see what it looks like from outside. This is where we are. So this is the sun. So we're about 8 kiloparsecs away from the center of the Milky Way. In the Milky Way, there are 250 billion stars. 99.9% of them can host planetary systems. So that's a whole lot of planets. And we know on average there's more than one planet per star. In our solar system, we have 8 planets. It's highly likely that the number of planets in our galaxy is 7 or 8 times the number of stars. So again, numbers. So if we look a little bit closer to home, we have people who are looking for technosignatures out there. So they're using this radio telescope called the Green Bank Telescope. And they're looking for technosignatures. So in the radio, they're looking for patterns. So something that nature can't explain. Okay. And they've currently surveyed around 1,300 stars looking for kind of these technosignatures. And they haven't found anything. If they'd found anything, you would have heard about it by now. But they are still trying. This is only a small fraction of all of the systems that they're going to look at. But if you compare this number of stars, it's a really, really tiny fraction of stars, okay? It's a really, really tiny fraction. So we haven't really even scratched the surface when we're looking for technosignatures. And then to place us in a little bit more context, so this is the solar neighborhood. So the sun is here, and this is the stars that are kind of sitting within a few hundred light years of us. So within 250 light years, we have 250,000 stars sitting in our kind of sphere. So we've been broadcasting for about 120 years, okay? Which means that we are only visible to stars or star systems within this bubble. You can call this kind of a bubble of visibility because radio waves travel at the speed of light. And this is 120 light years in radius. So outside of this bubble or sphere, we're not visible because the light that we've been emitting hasn't been traveled there yet. And we're only visible within this bubble. And this is a tiny, tiny bit of our Milky Way and a tiny bit of the solar neighborhood. Yet, if we look at our exoplanet detection statistics, of those 29 potentially habitable planets, 19 of them are actually sitting within 120 light years of us. Okay, so think about how small that bubble is. Think about the number of stars in the Milky Way. Think about the number of planets there are, and I'll kind of leave you to think about whether or not we are alone. And I'll finish there. And I'm sorry for all the technical difficulties. I'm very happy to pass over to Eric to give his thoughts as well and to take your questions after that. Thank you. So is Eric online? I don't see him. My laptop's about to die as well because I wasn't expecting to host Zoom. So maybe we should move to Q&A. That's okay. Yeah, I don't see Eric online. He must have had difficulty connecting. Yeah, sorry.
Well, first of all, everybody, thank you for
No problem.
Fascinating talk. I'm coping well so well with all the tech problems. We do have a few minutes for questions for anyone who has been doubted completely. Has questions to ask. I'm sure we're probably far more of them than we'll have time for.
Yeah, thanks very much. It's great. Well, two questions really. One is some of these worlds are, you said tens, hundreds of light years away. Other galaxies are considerably further than that.
Yeah.
So some of these planets may no longer be there, I guess. The farther out reaches of the galaxy and the solar, well, not the solar system, but the galaxy. The other thing is about error bars. There's sort of pretty large error bars in some of those data. I presume the new instruments are getting more sensitive, so those are going to be shrinking. So we can be more certain that the models are more robust.
Yes. So what was the first question?
The first question was, are we looking too far into the past?
We are really only scraping the surface. We're seeing now really in universe cosmic timescales. It's very difficult because the further away we try to see, the weaker the signal, and then we run into the problem that you've just said. You cannot infer anything really about that. So things that we are detecting are in our neighborhood in the galaxy, very much so. What we can extrapolate and say beyond that is, well, we have to extrapolate. In terms of the error bars, this is always what we have to worry about in astrophysics. We are dealing with very weak signals. We do a lot of, I would call, data manipulation to try to maximize signal to noise. We do that. That's, if anybody is an expert in data manipulation, it's astrophysicists. So the authors of all the spectra that I showed you would have done their best to fully to maximize the signal to noise. That's done by kind of binning and averaging the data to try and get, again, that's our if you wanted to claim a detection, you really need signal to noise of 5 or more, for example. JWST has brought all those error bars away down just because it's much more sensitive. But yeah, it's always an issue, is our signal to noise.
Our models are wrong, some models are useful.
Yes, and it's why we always do modeling as well. We have the data, we run models to rule in or out explanations. It's never that we say the model is the answer. It's just that we can say this model better reproduces the data rather than this one. So, an atmosphere with CO2 in it better reproduces the data than one without. These are things that we can say.
Yeah.
So, if I understood correctly, the last slide there, 19 of the 29 are within 120 light year radius.
Yes.
So our signals, our radio, TV was going out, and they could have seen this and sent a signal back saying, "We've seen you." Like the television stuff.
They could have done, but
Send more.
but this is it.
Or whatever.
It takes 100 years, right?
Yeah.
For that. So if they saw a TV show that aired in the 1960s, which was what 60 years ago now, if they relay a signal back, that's going to take another 60 years to get to us.
Yeah.
So I mean, these are things that are longer than a human lifetime. You put it, if you think about it that way. Yeah, but I mean, that's our techno signature bubble. This is when that's our techno signal bubble, right? We're not visible through our own own kind of transmissions beyond that light bubble. Yeah, it will expand all the time. Yeah.
Any more? Look at that.
I was wondering about the state of the art in terms of knowing the absolute or relative amounts of different components of the atmosphere. So you say it's got some water and some carbon dioxide, but obviously we know the Earth's atmosphere. Actually, what can you say about this?
Yeah. So
Can you redo the question, Catherine?
yeah. So the question there was, can we know something about the relative composition of the different molecules we're detecting in the atmosphere? The answer to that is yes, but with a caveat, it depends on the model that you use to simulate the data. So we know that atmospheres are not one-dimensional, they're not two-dimensional, they're not three-dimensional, they're four-dimensional. Every planet has a climate. And we are dealing with very weak signals that are one-dimensional in the sense that we're looking at a spectrum. So how complex we make our models affects what abundances we derive from the data. So a route one approach is just to assume the atmosphere is homogeneous, all of the molecules are sitting in a layer, they're all at a single temperature, and then you derive that abundance and temperature. But we know that's not going to be the reality. So yeah, depending on the model that you use to extract information out of the data, you can get different abundances. And this is huge efforts going on to try to figure out what's the best model to use to get the highest information out of the data. But it's a tricky one, yeah.
What have we got on chat?
So there's one question online. What are the chances of a DNA replicating molecule being formed just through chemistry? I would say that's less likely than, yeah. That's a good question. I don't know. It had to have happened at some point, right, in our past. Something must have happened to create this molecule. There's a big gray area though between, amino acids and DNA, right? And I think, yeah, I would need to ask a biologist, I think, to answer that question. Certainly we see simple amino acids in space. So we see glycine. Glycine was detected on 67P. So the same comet I showed you where there was DMS. In asteroids, meteorites that fall to Earth, we find amino acids in that. So that must have come from the parent body. So chemistry in space can make simple amino acids, but it's still a big gray area about how you go from that to self-replicating molecules and then life by extension.
One last question, Kirsten. I think we'll bring that to the last and we'll.
Great talk, Catherine. That really was inspiring. Just a little footnote on that last question there about DNA. So Francis Crick,
Yeah.
who shared the 1962 Nobel with James Watson and Maurice Wilkins for discovery of the double helix structure of DNA. In the 1970s, he published this obscure paper in the journal where he actually proposed, he was thinking about why is the genetic code here so pretty near universal reality. But in his paper in the 70s, him and biochemist Leslie Organ proposed that DNA had actually come here from outer space.
So panspermia, yeah.
They further, because you see one throwaway line in the paper where he actually said, the stuff when I read it, Crick actually sticks his neck out and he actually says, an advanced civilization may well have sent it deliberately. Yeah, well, I read it and I thought, seriously? Yeah, I've got the
But yeah, I mean, I would say that probably because at that time it could have been a plausible, you know, if you have no way, or you have nothing in your scientific language, for want of a better word, to explain what you're seeing, then yeah, from outside is a good explanation. But we do see, I mean, we do see kind of the beginnings of prebiotic molecules in space. We do. We see chemistry in space. It makes all sorts of stuff. It happens. The comets are particularly abundant in these complex organic molecules. So we know the chemistry happens and can build long carbon chain molecules. It can make polymers. It can make amino acids. Again, there's still a question about how do you take something that's your raw material and you convert it into something that looks like RNA or DNA. And that's where people are working very hard to answer that question. Yeah.
One last question. This really is the last.
I wonder to what extent we're barking up the wrong tree, because if we're talking about looking for civilizations, I can see one characteristic of our civilization is it is becoming slowly less biology related. Just on the screen here we have Zoom, which is an illustration of something that is happening in outside the reality of biology. As civilizations develop, I suspect that there'll be a tendency for biology to become less important.
In what aspect?
Yes,
And why do you mean less important?
there may be more
you mean
terms of life that is not biological.
I'm skeptical about that because, yeah, I'm skeptical about the rise of artificial intelligence. It's not smart. It won't take over humans. We've been using machine learning for decades to
I'm
do.
not saying this
Yeah.
is going, what's happened is something that.
Yeah. I still think that humans are still going to be, biological beings are still going to be important in the future, if that's what you mean.
That's exactly what I mean.
Yeah. So I'm skeptical. I think, yeah.
I think on that controversial note, which is beginning of a whole new debate.
Yeah.
Just want to say again, thank you very much indeed, Catherine.
Thank
I
you.
really
problem.
did enjoy a talk on a subject on which I know very little, but now feel slightly better informed.
Good.
So thank you again for
No
your
problem
time
at
and
all.
your
Thanks
effort.
everyone for coming and your very nice questions as well. Thank you.
Quick on. You want to talk about next meetings?
Yes, thank you. Just want to quickly remind you that we have another event later this month on the 25th about toxicology.